All right, welcome to our final Macomb meeting of 2019. Tonight we have frequent presenter Dave Bailey talking about neutron stars. Astronomy has always been a major part of Dave's life. His parents met at Yerkes Observatory. Dave is in the minority in the club because he's more of a theoretician than an observationalist. I'm not sure that that's actually a minority. I think it's about 50-50. He actually doesn't own a major telescope. As an optical engineer, he worked on several different kinds of spy equipment, details classified. He has done laser isotope separation, not on uranium. He has worked with laser weapons, both offensive and defensive, and nerve gas detectors, details not classified. Living up to his reputation as the club's resident Einstein, Dave's presentations to the club regularly expand our minds and challenge our preconceptions. So, welcome to the presentation. I hope you all have handouts, and we'll get started.
If anyone is missing a handout, I have 2 extras here. Anyone want one?
Does anyone? Anybody need a handout?
Okay.
Okay, first of all, some housekeeping stuff. If you got a question, I like questions in real time, because if you're waiting until the end to ask a question, by the time you get to the end, you will have forgot what you wanted to ask. So, and this is 5 pages. The presentation should be about 15 pages, but I haven't had time to process it all through and onto the paper. At the end, if we got lots of time to kill, I got this whole book about neutron stars. And so we'll probably have some questions at the end. Questions either about stuff that's in the handout or not in the handout. And we can throw up diagrams and such from this book on the screen if need be. So, up at the top here it says neutron stars and pulsars, question mark. Or spinars. There's this. Oh, let's get some pictures up on the screen. Right
There, it's already there.
Thank you. Sir, I imagine means that he's either a Brit or a Canadian.
Or in Australia. I don't remember.
And he discovered the neutron, according to this, in 1932. And nobody knew whether the neutron initially was stable or if it was radioactive. People only had a vague idea of what radioactive meant. They were blissfully ignorant. And like it says here, the words atom and atomic were well known, nucleus and nuclear less well known. The words fission, chain reaction, reactor, bomb, those words all existed in the English language, but they had nothing to do with nuclei. Unfortunately, those people eventually learned some nasty things. Okay, let's skip over this story about the tavern. You can read that. How about Fritz and Walter? Cool. And this one on the right, that's one of the classic ones. Zwicky loved to make faces when he saw cameras coming. And I've seen some that were even stranger looking than that.
He was a pretty quirky guy to begin with, wasn't he?
Well, yeah, I've got to talk to his students. I've never talked to a Zwicky student, but I'm sure they got all kinds of sea stories they can tell you about him. And you can see that he does have an actual face as well as the put-on face that you can see on the right. And oh, that's Zwicky also?
Me too.
Wow.
Younger.
It looks like he actually might be thinking in that one. So he and Walter Baade. Cool. Now, this guy is as conventional as Zwicky was outrageous. And the story goes that nobody would believe that the neutron star could possibly exist because Zwicky, who would believe anything that he thought up? So he got Bada to be his co-worker. And this guy was so conventional. Well, he believes that neutron stars exist. Well, maybe. So that was 1934. And it was known at this point that if it was possible for neutron stars to exist, they were going to be really strange. Not strange in the modern sense. Strange is a technical term these days. We're referring to certain subatomic particles, but strange in the old sense. And they were going to be super dense. And then there's a little section about the white dwarf, which was discovered 19 years previously. And essentially the same thing happened. People didn't think that white dwarfs could exist because their statistics were too strange. Again, that same word strange, which didn't mean anything technical back then. 1939, Oppenheimer and Volkov. There he is. Oh, and who's that guy on the left there?
Yeah.
It's you.
Oh, no, I'm wearing short hair. So here's some of the strange characteristics of neutron stars. An atmosphere made out of pure iron, vaporized iron, of course.
How tall will that atmosphere be? A couple centimeters?
You're cheating. Temperature of 1,000,000 degrees or so, gravity field of so many zeros I can't count them. A gas density of 5,000 times water. On the Earth, there is no possibility of having a gas or a liquid or a solid that has anything like a density of 5,000. This is a gas with a density of 5,000. So everything you think you knew about solids, liquids, and gases goes out the window. So you start talking about neutron stars. Yeah.
Why is the atmosphere made of iron?
Well, when you start fusing things, you can get energy out of them, and then eventually you end up with all of your stuff that you're playing with is in the form of iron. Now it's no fun to fuse them anymore because you can't get any energy out of it. So iron is sort of at the bottom of the energy / mass thing. So iron is sort of inert. You can't get more energy out of it by either fission or fusion. Volkov. Oh yeah, he was a collaborator of Oppenheimer's. And as it says here, they did design work. They designed neutron stars. And a magnetic field of so many zeros you can't count them all. And the atmosphere, as somebody said, is like here is the quote surface of the neutron star. That far down, conditions now are already way, way different from what they were there. And like it's like here's the neutron star, right? Well, let's try this one. It's like, there's the neutron star, and conditions from that edge of the line to that edge of the line is totally absurd. Things are so different there versus there. And this whole thing here is about the size of your hometown in Michigan. They're tiny.
Why are things so different, so close to the top?
Strong gravity. Strong gravity and you know, like it says here, you know, gas density of 5,000 times water, and incredibly strong gravity. Oh. So the question is, if things change so much from that edge of the line to that edge of the line, what do you suppose it's like down there? And the answer is, nobody knows. And who cares? Well, some people do care, and they maybe know something about what it might be like down there. And down here, you have not only neutrons, because everybody knows neutrons are made out of neutrons, right? Or else they wouldn't have used that word to describe them. Down in here, you have things like pi mesons. And why pi mesons? Because they act like electrons, but they're easier to deal with because the electrons are hard to compress because of degeneracy problems. Well, anyway, that's in another section of this. Then, after 1939, Oppenheimer and Volkoff were working on bombs instead of neutron stars. So nothing happened until 1967, when Jocelyn Bell, those are, okay, 2 black and whites and 1 color. Which one was taken last? We don't have a picture of her radio telescope.
Yes, it is. Right
Yeah, it's in the
back.
background.
Oh, no, that's the first one.
Oh,
Where is it?
Right in the
I
right.
think it's a dish.
Okay.
But her telescope was her telescope was 4 acres in size with 4,096 dipole antennas. It was anyway. She was not working on neutron stars. She probably never even heard of them. And she was getting this little bit of interference. And the interference repeated every 23 hours and 56 minutes, which is how long it takes the Earth to go to orbit, to spin once and get back to the same sky view. If it repeated every 24 hours and 0 minutes, then the interference was very likely an Earth thing. Like somebody flipping a switch every day at exactly noon, that kind of deal. But she figured out that, hey, this has to be out in space, because 23 hours and 56 minutes is how long it takes the Earth to go around, to rotate once in sky coordinates. And so then she looked a little more closely at the signal she was getting. And it wasn't like shh, it was like beep, 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 beep. And she says, holy cow, somebody's sending bips at me.
Thanks, Jonathan.
What?
Hold on.
We found a picture of the
Yeah, we did.
actual.
I'm gonna put it in.
Oh, good, cool. Oh, well, just like a whole bunch of dipoles connected to a whole bunch of lead-in wires, right? 4 acres worth. There they are. That doesn't show all 4,096 of them though.
No, but it shows you a representative sample.
Yeah. And according to the story, it took her 2 years to set that up. And I'm thinking, she's a graduate student and she's just wasted 2 years of her graduate education building those things. Well, I don't know, I guess that's the way they did things in England at the time. So, cheap labor, right?
What year was it?
67. Yeah. And the period of the pulses was 1.337311 seconds. Now, you're not going to tell me that that's natural. If it repeats every 1.337311 seconds, that's an artificial machine putting out those blips. So, but they couldn't find anything that, any human interference that was doing that. And then she ran into 3 other places in other parts of the sky where she was getting blips, and one of them was 0.25 seconds, so and so on. And for a while she was thinking that these are the space aliens. They're sending bips at the Earth. But when she discovered there were 4 bunches of space aliens in 4 completely different parts of the sky, then she said, okay, well, either the entire galaxy is trying to communicate with me, Jocelyn, here on the Earth, or much more likely, they really are some kind of star out there. But what kind of star? Who knew? And it turned out to be way stranger than anybody thought, except for certain people like Oppenheimer and Volkov, who knew how strange it was going to be, but they weren't telling because they were working on bombs.
And Oppenheimer is dead.
And Oppenheimer is dead. By that time he was, I suppose, 67?
Yeah.
Okay. Yeah.
In fact, he died in 67.
Oh, he died in 67? Okay. So, then they realized that maybe they are really small stars. They have to be really small because something the size of, say, Jupiter, which is already smaller than practically every star, something the size of Jupiter isn't going to go bip every 2 seconds or even every 1 second or anything like that. So, it had to be something really small. And they had to be either something that is spinning around or something that's maybe expanding and contracting every 1.33 whatever seconds. But, okay, this is huge. This is Jocelyn's co-worker. I tend to think of her as the discoverer, so he's just the co-worker.
That got the Nobel Prize and she didn't.
Well, yeah, of course. It has to do with the DNA. Nobel
Well,
Prize
at the time,
DNA.
that's what the Nobel Prize was.
It's on the Y chromosome, the
It pretty
Nobel
much
Prize.
was what, she got screwed by that, really.
Yeah. So, gold. Can we see gold? Well, I see a
Again.
piece of gold, but that's not what I'm looking
Tommy
for.
Gold.
There we go, Thomas Gold. And he's an American? Is that
Yes.
right?
Well, he was Austrian born, but he was a professor of astronomy at Cornell University and a member of the U.S. National Academy of Sciences.
I always have him do the bio stuff for me because he can do it way faster and way better. Thomas Gold,
This is the same year, by the way, this is 1967 that he really did his work as well. So,
yes,
yeah.
less than a year after the discovery
Right.
of this mysterious bipping machine out there. And he was I forget where he was, he's American anyway.
He
Columbia?
became an American, yeah.
Columbia?
Cornell.
Cornell,
Cornell,
one of those
right.
C places.
He escaped Hitler when he came into Belgium and France.
A lot of people escaped Hitler by
And that way he got out.
days and sometimes hours.
This was what it was. He said
Yeah.
he was out, he was actually interned for a while, but he did get away.
And he said that these supposedly things are called pulsars couldn't actually possibly be pulsating objects. Because he figured it all out. He tried to figure out how to make a star expand and contract like that. Flip, flip, flip. It just wasn't working. But making them spin, that did work. And the way you did it was, you got this thing which has a north pole, there's the north pole, and there's the south pole, and it's spinning around every 1.3 seconds, or in some cases every quarter of a second. It's got a big, hefty magnetic field, just like the Earth's magnetic field, except that Earth's magnetic field is about 1 Gauss, and this is about, let's see, 10 to the 12 is a
Yeah. Trillion?
trillion,
Trillion.
Trillion? Trillion.
and maybe even 10 to the 13 Gauss. And-
Quadrillion.
And so we got a huge, humongous North Pole there and a huge, humongous South Pole there. And this thing is, none of those magnets are lined up with the spin axis of the object. So the North Pole goes around like that, South Pole goes around like that. And then we got a bunch of field lines coming out here, and a bunch of field lines there, going like that. And then if you blow this up, or not blow it up, if you shrink it down a bit, here is the neutron star, and it's going around like this. And then you draw a thing out here, which is called that's the light cylinder. And if you have objects fastened to the neutron star that go out here, let's say you got the equivalent of space probes, except that they're fastened to tall towers, right? And don't ask me how to construct this thing, since all the temperatures are in the millions of degrees and sometimes billions of degrees. These things are going around almost at the speed of light, because this is the North Pole and it's going around like this. And since this is the light cylinder, anything that's outside of this, that's fastened to the neutron star, has to be going faster than light, which is impossible. So people got the idea that strange things happen out there near the light cylinder. And in particular, if this is the magnetic field, this is that humongous magnet that I was talking about. Out here, you get field lines that are going like that, because they all connect into there. And likewise here. And out in this region, atoms and molecules, which have been fastened to this neutron star, they're in a really strange situation, because if they're going out there, something has to happen. Like if their magnetic field lines connect to here, out there, the magnetic field wants this object out here to go faster than light. Well, that can't be. So the field lines get all tangled up. Instead of going like this, they're going like, they're like spiraling. This thing is turning this way. Everything is, so out here you got a thing that sort of looks like a spiral nebula. Like if you're looking at this from above, there's the light cylinder, and you have magnetic field lines that look like that. and they have to be tilted at angles at least as much as that, because if they were straight like that, then that part of the magnetic field would have to be going faster than light. Even magnetic fields can't go faster than light. So everybody knew something was strange happening out here. What was strange? Well, energy was being sent out, and you ended up with a cone that looked like that, and radio signals were going out along that cone, and this wrap process here, I can't show it here because of I can't show this in 3 dimensions properly, but so radio energy is going out along this cone, and this thing is going around every quarter second, say, and any planet that's more or less in that direction, or in that direction, or in that direction, or in that direction, is going to hear those bips. Any planet out here, no bips. Any planet right on the spin axis, no bips. So people started to realize there's a lot more of those things out there than we realize, because most of them can't send a radio bip signal to the Earth. That's interesting to know. And these things are so tiny. That's also interesting to know. That is 20 kilometers more or less in size. That's, well, it's bigger than a Michigan township, I guess, but it's smaller than a Michigan county. It's a little thing. And these things are really, really hot. They're way, way brighter than any star, but you can't see them. Why can't you see them? Well, they're very, very bright, but they're very, very tiny.
Very tiny.
Interesting.
So the frequency of the blip reflects the speed of rotation?
Indeed it does. And they slow down.
There's also an interesting thing about Thomas Gold that you should know.
Yeah.
In 1948, he was one of the first to put forth the steady state theory, and which George Gamow and a couple of the others said, no, it's a Big Bang is what they wanted. And it's very interesting that he took a lot of heat for that, and then he kind of shifted his thought process to neutron stars and pulsars and things like that. But
Yeah, well,
initially,
Einstein went around that loop
He did
because
too.
he had this famous lambda, which was the cosmological constant, which he, at first the universe was expanding, and then he said, well, we can't have that, so he put in lambda to make it not expand,
Right.
and then he discovered, oops, I was right the first time because the universe is expanding, and everybody said, oh, look, we caught him in a boo-boo. Well, you're welcome to use the word boo-boo in connection with Einstein, but
you could. Speaking of Einstein.
most of the time Einstein's going to be the one that's right, and you're the one that's making the boo-boo, probably. Oh, there he is. Yeah. Guess where he got the idea of sticking out his tongue when he saw a camera? From Sticky, probably. And his tongue was a lot longer than Sticky, so he could out-Sticky easily. And there's more than one picture like that. I suspect that sometimes he would see more than one camera, so he'd just stick out his tongue once and it'd be click, click, click. Yeah.
Notice he's born on Pi Day.
What did you say?
He's born on
Born on
Pi
Pi
Day.
Day.
Oh, yes, indeed. Indeed, yeah, that is true. March 14th.
But it goes wrong in the 5th digit.
Yeah. And I've got a number here for you. This is another neutron star, if I can find it. Let's find it. Probably on the last page. There we we go. There's a neutron star that goes around in about 1.6 milliseconds. So its period is 0.00 1 5 5 7 8 0 6 4 4 8 8 7 2 7 5 seconds. If you're going to do research into pulsars in the lab, you better have the best clock that you can lay your hands on, because the thing you're comparing your clock with is this neutron star that has that many digits in its period. And if you focused in on this number 6 and made that 6 into a 7 and just left it as a 7 for 1.5 milliseconds and then put it back to a 6 again, what you had done was essentially the equivalent of moving your clock 1 foot closer to that thing out in the sky. Or you go from a 6 to a 5 for 1.5 milliseconds, and then put it back to a 6 again. Now you've moved your experiment 1 foot in the opposite direction. This thing is unbelievable. If you took that 5 and made it into a 4, how long would it take before your equivalent location for your clock had moved a foot? And the answer is 1 hour and 3/4. That being a 4 instead of a 5 means that your clock is moving this way, and in 1 hour and 3/4 it will have moved a foot. That is amazing. And the neutron star out there in space has no idea that it's being compared to an alleged atomic clock that is allegedly perfect. It's being perfect just on its own. Now it's slowing down. How long does it take to slow down by 1 part in a million? 470 years. It's essentially spinning at a constant rate. Except, well, in 470 years it slows down by 1/1,000,000th. So, these things are amazing. Pulsars. Some pulsars can be observed in radio, visible light, and X-rays. Some can only be observed in radio. The pulsar at the Crab Nebula is visible. It flashes every 33 times a second. And it seems to be on about 50% of the time and off about 50% of the time in the pictures I've seen. But I think it was discovered first in visible or in radio. I don't happen to know.
Thought it was radio.
If you look at the actual waveforms, you discover that some of them are very uniform. Here is noise, and then it goes like that, and then noise, and then way out here it goes like that again. And some of them they look like this. And then the next pulse looks like this. And you say, oh, look at that. The pulses, they match, except that this one's smaller this time than that one was. And this one is now the same height as those, and this one is bigger. Oh, what do we got there?
That's a pulsar.
That's Pulsar, okay. And it's got some kind of head sticking out from it. Is this Pulsar here? Or is
Down there.
Is it down there? this is aligned up with it, so I was thinking maybe that's the
Could be.
pulsar. I don't know.
My money would be on that.
Now, the interesting thing about this one is, if you look at an adjacent radio frequency, you see this. And you say, oh look, there's the blip, but it moved over. You look at another adjacent radio frequency that's a little bit farther down the band, it looks like that. And you say, holy cow, this is the same signal, delayed a little bit. That's the same signal, delayed a little bit more. And you say, look, it's just going through outer space. What's delaying it at different frequencies? Well, the interstellar medium is not a vacuum. There's stuff out there. And it can slow down the signal so that it arrives a little bit later than you would have thought. And if you tune up the band, it looks like this. You could have predicted that. This is now in the, we're off the end of the handout already, pretty much. Some of these, you got a blip there, and there's another blip there. They come in all shapes. Like this one is taller than that one, etc. And if you plot where that tallest one occurs, and then, well, these things can move relative to each other, but they usually don't. The more you talk about it, the more complicated it gets, because you make a statement, you say, and this is the way it is. Oh no, but wait a minute. In a lot of cases, it's not true, and so on. So these things they're almost like fingerprints. So you can see all these shapes I showed. That one is different from that one, which is different from that one.
So what did they tell us?
What do they tell us?
Yeah, so we've got to the point where we know what they are, but we've got, they
Well-
discovered in '67, here we are 2019. What do neutron stars mean to us?
Well, they make a pretty good lab, actually. If you have a binary neutron star, like, well, I gotta get rid of this because I want to be part of the blackboard. And you have a neutron star which is orbiting around another object. And let's just say the other object is relatively massive and large. There's a neutron star, and it's going around like this. And it's so close that, from the point of view of special relativity, it's going a good fraction of the speed of light as it goes around. And when you got objects moving at a good fraction of the speed of light, like maybe 1% of the speed of light, already at 1% of the speed of light, you have to do special relativity to keep track of it. But in addition to that, it's down in the gravitational well. Like if you try to pull it out, you have to do a lot of pulling. Accelerate it, it spirals outwards. And as it spirals outwards, the clock changes. If you lower an accurate clock down into a gravitational field, the period of the clock actually changes.
There's a chart that you.
That's a general relativistic thing. Yes?
It'll come right up.
What?
It's coming up.
Oh, okay, cool.
Go ahead, keep going, it'll get there.
Yeah. See how great it is to have him there? He says, oh, I've got a thing you gotta see.
I'm not sure.
Cool. So, what we got here is we have an extremely accurate clock suspended in an extremely strong gravitational field. Well, that's a general relativist groupie's wet dream. Wow, look what I got here. I got an incredibly accurate clock in an incredibly strong gravitational field. And it's spiraling downwards. In another few years, it'll be there, and another few years after that, it'll be there. And you know how you expect its period to change, but you keep going lower and lower, and the gravitational gradient keeps getting stronger and stronger. You're doing an experiment in general relativity, just with your telescope and your radio telescope. That is so cool. You can also look at these things, look at the slope of that line. That tells you how much stuff there is out there. And if you know how much stuff is there per cubic light year, you can calculate how far away that pulsar is, because if there was twice as much stuff out there as you thought, this blip would be there, this blip would be there, and this blip would be there, and the line through them is like that. So you're monitoring the interstellar medium out there by looking at the slope of that line as time goes by.
So,
Yeah.
well, you said the orbital speed is close to the speed of light?
Well, if you keep going farther and farther down, yeah.
Isn't that the definition of an event horizon?
Yeah, if this is a black hole, then
Oh, okay,
I
now
just
we're
erased it, so
getting-
I erased it for a
Are
reason.
you talking about black holes or neutron star? That's that's
Yeah.
kind of what's in my
Yeah.
mind.
Well, neutron stars aren't quite dense enough to be
Yeah,
black
yeah,
holes.
That's right.
Now, there's an event horizon, and anything that you think, quote, happened down in here, you will never know about.
Right, right.
And it's a philosophical question. You think that something happens down there? And I say, no, it didn't happen. You say, oh, yes, it did. And they, no, it didn't. Who is going to win that argument? It's down below the event horizon, so nobody will ever get any information from it. It's a philosophical question. Did it happen? Did it not happen?
So Schrodinger's cat.
Well, in a way, yeah.
It happens in a black hole, stays in a black hole.
That's right. But it didn't happen. It didn't happen. That's the whole thing. And you can't say I'm wrong. And I can't say you're wrong when you say, oh, yes, it did happen. It's outside of our universe. And people say, what do you mean? It's outside our universe is a huge thing. This black hole's a teeny tiny thing. How can that be outside our universe? Well, it is outside our universe. It's disconnected from us. Say, well, I can find out whether things are happening down there. All I gotta do is go down there, fall into there with my spaceship, and see what's happening down there. I say, fine. When are you gonna report back?
So now we're
Well,
talking
I
about the
don't
black
know
hole.
about that. It might take me a while to report back. I say, you will never report back. You can fall into an event horizon, you cannot fall out of an event horizon. Yeah, what do we got?
That is actually the diagram that was originally written in 1967.
Oh, cool. There it is. There's a little bit of fuzz. I forget what term she used for it, but it was, there we go, there it is. And that's a quarter, this is 1 inch. And she's pouring over this. And you can imagine how many inches of
1 inch
chart
means
paper.
1 inch represents what?
Time? I don't
Well,
know.
it's gotta be a time element, right?
Yeah.
1 inch of
It's on the T
rotation.
scale, it's on the time scale.
Yeah.
Yeah, the paper goes, well, right here.
Yeah,
1910,
there you go.
1920, 1930. So this is probably 10 seconds.
Okay.
So this is, that's about 1 second worth of paper. if we're right, it might be a minute, might be a second. It's something that comes out even. If it doesn't come out even, she's gonna go crazy. That's
So what
clear.
causes the difference in amplitude? I mean, the mass of the mass of the neutron star doesn't change. I mean, that's so doggone. I mean, there's no flexibility in the neutron star.
Well, it's slowing down. It's slowing down because it's sending radio signals out into space.
Yeah,
Those radio signals have energy.
so that's what
E
causes the
equals
amplitude.
mc squared, right?
Right.
And you can calculate how much energy is going out. And by E equals mc squared, now what you're interested in is in the mass. So m equals E divided by c squared. Easy enough. So we know by just looking at our radio telescope information how much energy we're getting. You divide by the square of the velocity of light, and that tells you how quickly that neutron star is losing mass. It's losing mass because it's sending out stuff that weighs something. Now, the photons in that radio signal have 0 rest mass, but they do have mass because of E equals mc squared. And in fact, there is, I think that's one of the things I printed in here. If I can find it. Yeah. Next page to the last, on the left side. There's a little chart that shows pre-supernova mass. And there's 4 stars that one of them is 13 times the mass of the sun, and one of them is 25 times the mass of the sun. Those 4 all have supernova explosions. And just after the center of the star collapsed, a pulse of neutrons go out. Like not neutrons, pulse of neutrinos go out. Like the neutrinos that were detected after supernova 1987A, which was observed by the people down south, around Australia and so on. And that pulse of neutrinos, 20 of them were detected. Some of them in Japan, some of them in Ohio, and some other people thought that they detected some. The people in Mont Blanc were probably wrong, and so on. Anyway, 10. How many was it? 20. Excuse me, 20. 12. I think the Japanese saw 12 neutrino detections, and the people in Ohio detected 8. So that's 20 of them.
There's the supernova.
Yeah. This is called the Tarantular Nebula. It's the most spectacular object of that sort in the entire sky, especially when you consider how far away it is. It's in another galaxy, Large Magellanic Cloud. This one is a supernova, right?
Right, 1987A.
Yeah. It's a type 2 supernova, which means that it came from a core collapse of a massive star.
Mm-hmm.
Well, isn't a population 2
If it's a population 1, then it can be a white dwarf collapse.
white dwarf?
Yeah. And I'll do a little demonstration. You people are part of the outer parts of a highly evolved star, and I'm in the central regions, and things where I am are so dense that I'm about to collapse. And here's the place where I'm going to collapse. And down here, the collapse can start very suddenly, and in only 1/10 of a second, it can collapse enough so that a supernova is sure to happen, and a neutron star, in some cases, is sure to form. Now, somebody in the back, you want to grab my hands and prevent me from doing that. You can't do it. You're too far back. If you were gonna stop me from going like that, you'd have to be going faster than the speed of light to get to me, grab my hand and stop me from doing that. Actually, of course, my hands are going together considerably slower than a tenth of a second. These collapses can be extremely sudden and extremely fast. And that demonstration goes to show that what counts in core collapse is not the mass of the star, it's not the size of the star, it's not what you people out there are made of. You could be iron and you could be made out of helium. Doesn't matter. What counts is right around here is what counts. And so a lot of the stuff that's in these books you have to discount because they tell you what the original mass of the star was. Oh, a few million years ago it weighed 20 times the mass of the sun. Well, okay, what does it weigh now? Well, it weighs less because it's lost mass. Okay, but that's back there. What counts is what is it like right around here. And once you realize that, you learn that a lot of the stuff in the neutron book, you don't have to read it because this is all about the star as it was long ago and far away.
So we've got about 10 minutes left. Are there any more questions that people want to lob at Dave?
Of course.
Because he can probably take up 10 minutes and one answer.
Well, we'll see about that.
I have a question. How would a Thorne-Zwickau object develop?
Yeah. I'm only vaguely aware of those things. I
What is it called?
believe it's Thorne.
Neutron stars.
Thorne with an E.
Yeah, Thorn with an E.
Thorne with a Z. Z-Y with a dot over the Z or something. It's some, maybe a Hungarian name. Zwickau or something.
So Thorne with a Z.
Yeah, there it is. Thorn
Cool.
Zwickau.
There you go, right there.
There it is. Where's the dot?
Don't,
Oops, there we go.
There's the dot over the Z. Okay. And basically you got a red giant or a supergiant and a thing like a neutron star. There we go. Once the neutron star enters the red giant, whoa, that sounds like a bad thing.
So the overall mass of a neutron star, how does it compare to, say, just
Oh,
an average star?
If it goes beyond about
main sequence?
If it goes beyond about 3 times the mass of the sun, it does that, it collapses into its own personal black hole, never to be seen again. So that's the maximum mass for a neutron star. More or less 3 times solar masses. It might be 3.4 solar masses, it might be 2.9 solar masses. Nobody knows except for people like him who do the theory stuff.
So I see the Tolman-Oppenheimer Volkov limit that it talks about it during the course of this binary collision. Is that
Yeah. Probably.
the result of what Oppenheimer and Volkov were contributing to
That's a good question.
neutron research?
I'm not sure how much of their stuff that they did back then is still considered relevant today. I wouldn't be surprised if a lot of it is.
There's your Tolman.
There it is. Okay, so analogous to the Chandrasekhar limit for white dwarfs. So that's
Yes.
2.17 solar
The
masses.
Chandrasekhar limit, everybody knows that it's 1.44 solar masses. No, not true. There's a whole bunch of correction terms that have to go in there. Sometimes the correction terms get as low as 1.09 solar masses. Wait, whoa, 1.09, 1.44? That's a major difference. And Chandrasekhar will simply say, well, my paper back in 1939 or whatever it was had some assumptions in it, and I still go with those assumptions. Of course, he's dead now. But Chandrasekhar was at Yerkes Observatory when my parents were there. And he was kidnapped by his grad students one night because he had said many times in lectures that he was a theoretician and that he had never actually looked through a telescope. Well, one night, when it was good enough to observe, but not good enough to do any actual, productive work observing, they walked into his office where he was working, about to go to bed, and say, come on, we're going to go and observe. He says, I can't help you. I'm not an observationalist. And I said, tonight you will look through a telescope. And he pretended like he was incensed that he was being kidnapped. And they led him, you know, hand in glove, they led him to the 40-inch dome, and he looked through a telescope for the first time. And he pretended like he did not enjoy it. And in reality, of course, he's saying, wow, look at the grad students I've got. I've never had a bunch of grad students like this.
There's your 1939 reference.
I'm not sure whether my parents were there at that time or not. They ended up in a chicken coop from which the chickens had been evicted in Tucson, Arizona. And they were grad students in Arizona. Then they got this letter, mysterious letter. And down at the bottom was a signature, Franklin Roosevelt, a rubber stamp, no doubt. And it invited them to go to Cambridge, Massachusetts for an unstated purpose. And I said, whoa, if the president doesn't know what it is, it must be awfully secret. So they went there, they arrived, they just packed up and went to Cambridge, not knowing what to expect when they got there. When they got there, they discovered they were not astronomers. They were both radar engineers. And that's what they did for the rest of the war. My father was one of the first people to do a radar bounce off the moon. He may have been the first, because a whole bunch of people were doing it. It was one of those ideas that just suddenly was out there and said, look, our radars are limited by the horizon. They can see aircraft. The higher the aircraft fly, the farther we can detect them. Let's shoot it at the moon, for God's sake. And my father was getting pulses back, but he never got them synchronized well enough to take a picture of the scope traces. But other people are doubtless doing the same thing.
Nice list over here of the most massive neutron stars and their distance and stuff.
Yeah. I guess I saw you first.
All right, you say that in a supernova, the neutron star forms before the supernova
Well,
explosion
you saw me clap my
starts.
hands. That's the neutron star formation. But and it took 3 hours for that to ripple its way out to the photosphere of the star.
So this is only in a type 2 supernova?
Type 2. Yeah.
So
Because they type 1
I was under the
supernova
impression
typically-
that you basically get an iron core
Yeah.
and it rings and that kicks off the supernova. So is that ring what makes the neutron star? It's like the loudest bell
the
that ever tolled.
Yeah, but the neutron star is this tiny thing. And it's like the core. It's like the core is this big, you know, and it collapses. I'll eliminate the black hole because I don't want to confuse us with facts here. So there's the iron core starts to collapse, and the iron core is that big. The thing that's going to be the neutron star is that big. How can it possibly influence anything outside of itself? It's its own little world in there. It's like I said, you know, I go like this, and you people in the back can't stop me from doing this because I'm this little tiny thing, and I collapse in less than 1/10 of a second. Yeah.
I'm wondering if you'd like to discuss how much of a neutron star you can see.
How much? Well, we talked about that. It's hotter than any other star, but it's also tiny. So,
No, like, what percentage of the surface can you see?
oh, I would guess you can see all of it. Because if you launch some light from back here, it's gonna go around like this, and it's gonna end up, you're gonna see around the back side of it, I'm thinking. Because this thing is not that far from being a black hole, you know. And if it's a black hole, then you can launch some light towards a black hole, and some of the light just goes into the black hole and that's gone. Some of the light that just about misses goes around like this, and it could go around and around and around and around. And it's orbiting just on the edge of going into the black hole. if that kind of thing had happened, you can certainly see all parts of the black hole because some of this light, reverse time for a minute, and launch some photons from out here, and they spiral around and around and around. They gradually spiral out and they to your telescope. So I think the answer is you can see all of it.
So what would happen if a star, if they were to come into conjunction or
Oh,
a nearby star?
Well,
It should
there
bend,
is-
it should bend the light, right? Like,
yeah, yeah,
bends the
yeah.
light?
And there's a thing called an Einstein ring.
Yeah.
An object out here can, I'm trying to draw this in a curved way. And this is about more or less parallel, and it's going to converge on your telescope when it goes a few more thousand and maybe million light years. And you see this ring in the sky. And if you know what an Einstein ring is supposed to look like, typically it'll be stronger there, and it'll just barely be visible there, and like that. You say, I bet that's an Einstein ring. And you say, it's bound to be a large mass right there. I wonder what it is. But you can't see it.
But these are so small, so.
Well, you don't know how big it is, because it could be a neutron star, or it could be a fairly large object. It could be a globular
Right.
cluster. Who knows? Who knows? But what you have to have is you have to have a really bright light source there, or else you wouldn't be able to see the Einstein ring.
Well, I think we've hit our own Chandrasekhar limit, and we're all about to,
Oh, it's 9:30.
yeah, 9:30.
Yeah.
So, Dave, will you be going to the Coney Island tonight? If
Of
people
course.
want to continue the discussion
Yeah.
with Dave at the Coney Island on Van Dyke, just north, National Coney Island, Van Dyke, just north of 12 Mile.
And let's thank our speaker one more time.